Let's talk about gases. I'm going to start with a question. Why is it more difficult to breathe in Butte, Montana, or any other mountain town than in a coastal city like Seattle or Portland? Pause the video and write down a few reasons. You may have come up with a few ideas. That list could include elevation, which would be an important factor. Maybe you have an idea that there is less air at higher elevations. So let's break it down. When you breathe, your body is receiving oxygen. Oxygen is a major component of our atmosphere, which contains about 78% nitrogen, 21% oxygen, almost 1% argon, and many other gases like carbon dioxide, water vapor, etc. These percentages are mole, pressure, or volume percents. Provided conditions are constant, the mole percent in gases, the mole percent will equal the pressure percent, which will also equal the volume percent. This is a very handy relationship to remember. We can also express atmospheric composition as fractions, so 0.78 nitrogen, 0.21 oxygen, and 0.01 argon. We would call these mole, volume, or pressure fractions. You can divide the percent by 100 to obtain the fraction, or you can multiply the fraction by 100 to obtain the percent. In this course, I'll use N as a symbol for moles, V as a symbol for volume, and P as a symbol for pressure. In these fractions, the subscript of X refers to the gas of interest, and the subscript T refers to the total gas present. So an X, for example, could be oxygen. If we go back to our original question, why is it more difficult to breathe in a mountain town versus a coastal town? You probably already have an idea that there is less oxygen in the mountain town. Does a mole fraction of oxygen change at each of these locations? No. That's relatively constant in the troposphere. So what is it? Let's switch to math mode to find out. So if we know that the fraction of oxygen in the atmosphere isn't changing with elevation, we might have an idea that maybe this change is due to a change in concentration or mass concentration. So let's calculate the mass concentration of oxygen in Butte and Seattle. So before we start this, we're going to need to make some assumptions. So we're going to assume 21% oxygen in the atmosphere, which is pretty close to what it is. And we're going to also assume a temperature of 0 degrees Celsius. For the sake of this, this example, I'm going to keep the temperature the same in both places. So we know that at standard temperature and pressure, 1 mole of gas takes up 22.4 liters. This is a constant that I would recommend you memorize. So at STP, which is 0 degrees Celsius and 1 atmosphere, 1 mole of gas takes up 22.4 liters. And this is true for all different types of gases. It doesn't change with different gases. And this is derived from the ideal gas law. And I would recommend you do that derivation. And check me. So Seattle is at sea level. So we'll assume a pressure of 1 atmosphere in Seattle. So Seattle at 1 atmosphere. So basically Seattle is at STP. So we'll start with this 21%. So we'll say that there's 21 moles of oxygen per 100 moles of air in Seattle. We know that 1 mole of air has a volume of 22.4 liters. And then I'm going to convert that liters to meter cubed. So there are 1,000 liters in a meter cubed. Another good thing to memorize. And so we get a molar concentration of 9.37 moles of O2 per meter cubed of air. If we wanted to take that a little further and get a mass concentration, we could take that 9.37 moles of O2 per meter cubed of air and multiply it by the molecular weight of oxygen, which is 32 grams per mole, and we would get 300 grams of O2 per meter cubed in Seattle. Okay, and I would say, yeah, okay. So in Butte, Montana is at a lower elevation, I'm sorry, a higher elevation. Butte, Montana is at a higher elevation than Seattle, and it is at a lower pressure. So we will say that in Butte, the pressure is 0.85 atmospheres. So lower pressure than Seattle. In this first example for Seattle, we could use STP, the molar volume at STP, that's 22.4, but we can't use that in Butte because Butte's not at STP. So we need to use the ideal gas law to calculate the molar volume. So ideal okay, so if you'll remember from chemistry, PV equals nRT. And our molar volume is going to be volume per mole. And so we just rearrange. That's RT over V. We're at 0 degrees Celsius, which is 273 Kelvin. And then we're at 0.85 atmospheres. And if we're to do this, you would get 26.3 liters per mole. So this is small, or this is bigger than the 22.4 at STP because the pressure is smaller. So this is going to be larger than the 22.4 liters per mole at STP because the pressure is lower. Lower pressure, larger volume. Then we do the same kind of calculation. So we've got 21 moles of oxygen per 100 total moles of air. And then now in this example with the lower pressure, 1 mole of air is 26.3 liters. I want to convert to meters cubed, and there are 1,000 liters in a meter cubed. And then I'll go ahead and just use the molecular weight of oxygen, which is 32 grams of oxygen per mole. And I end up with 255 grams of oxygen per meter cubed in Butte. So what we see here is that Butte has the concentration of oxygen in Butte is 85% of that concentration of oxygen in Seattle, which kind of corresponds to the pressure in Butte. We assume that it was 85% of the pressure in Seattle. Finally, you may have thought the difference between air in a mountain town and a coastal city has to do with pollution. You may be correct, as many pollutants do make it more difficult to breathe. And maybe you were thinking of a particularly polluted coastal city. Let's consider ozone. The primary ambient air quality standard for ozone is 0.07 ppm. ppm here refers to parts per million. You can think of it as 0.07 parts or moles of ozone for every million parts or moles of air. We could also express this number as parts per billion by multiplying it by 100, or 1,000, and it would be 70 ppb, or parts per billion. We can convert 0.07 ppm into a fraction by dividing it by a million, and this would be a very small number. It makes sense because there's very little ozone in the troposphere. In fact, most places would have an ozone fraction even lower than that, because most places would meet the ambient air quality standard. However, even a very small amount of ozone can lead to adverse health effects, including difficulty breathing. So how do we decide which units to use? This is easy when you're doing some quick problems in class or on a test, because the units are normally specified in the problem. That makes grading easier. But what if they're not? In general, we like to use units that limit the need for scientific notation. So if we were to go back to the examples presented in this video, you would use a fraction or percent for something like nitrogen or oxygen in the atmosphere, and you would use ppm or ppb for something like ozone. If, for example, you expressed oxygen in terms of ppm, then you would have a huge number that would be very difficult to understand. Likewise, if you expressed ozone in terms of a volume fraction, then you would have a very small number that would also be difficult to understand. So that brings me to the end of this video. Here are some major points to remember. First, when you're converting between fractions or percents and mass or mole concentrations for a gas, you have to consider the molar volume of the gas at the given temperature and pressure. So you can memorize the molar volume of a gas at standard temperature pressure, STP, and that's 22.4 liters. But you'll need to calculate the volume of a mole of gas at other temperatures and pressures using the ideal gas law. These conversions are a little tricky, so don't forget to practice.